Hi, my name is Dirk Steiner with Yxlon, and in this video I want to talk about a very important parameter of industrial CT scanning, and that is the focus detector distance, so the distance between the X-ray tube and the detector. Some systems allow you to change that, to vary the distance, and the physical law behind this is the inverse square law, where if you look at position 1, in our case it's going to be 550 millimeters, and the dose rate per area is 1. And if you change the focus detector distance to 1100 millimeters, so it's twice as far away as the first position, the dose rate will only be a quarter. So with the change from 550 millimeter to 1100 millimeters, you're going to drop the dose rate per pixel at the detector to a quarter. And what it means in real life is what I'm going to show you in a few seconds. So we're here in Hudson, Ohio at Yxlon's lab, and this is a FF35 CT system. And I found this carburetor for leaf blower, and I thought this is probably a good sample. It has, the size of a little over an inch, maybe an inch and a half. It has like brass tubing and some stainless steel and aluminum casting and gaskets. So we have a dual tube system here, so we have the ability to switch between nanofocus and microfocus. For this we're going to use just the standard directional microfocus tube, and as you can see I already loaded this onto a block of foam, and that's a good position and that's good material that we use on a regular basis to do our CT scans. So the first shot we're going to do as I said, at 550 millimeters. So let me set this up and move the manipulator for that first scan. So now I moved the detector to our 550 millimeter position. So that's 550 millimeters distance between the focus spot, the X-ray tube, and the detector. You can see how close this is, and this is going to make the difference. So the main reason you want to do it is speed. So now with this close, you get a lot more dose per pixel. So that means you can run the detector a lot faster compared to where it would be on, all the way back. Yeah, let's close the door and get this scan rolling. All right, so we have the carburetor loaded, and we see it on the screen. We're at 550 millimeter focus detector distance, and well, this is probably a good shot now. It's right in the middle, and I can rotate it with the two fingers here, and it's not rotating out. I'm shooting at 200 kV and 200 microamps. I'm using the detector in the bin mode, so it's a 2x2 bin mode. We're taking 2070 projections, and we do a quick scan, so that means continuous rotation, so no stop and go. It continuously rotates the object on the turntable, and we have a voxel size of about 100 microns, which is for our purposes probably good enough. I'm gonna hit the start button, and here it goes. We'll see you at the evaluation station in just a second. So now as for the second scan, part is the same position. We just moved the detector back to 1100 millimeter focus detector distance. So you can see it's way back. It was right here for the first scan, now it's way back there. And we're going to set up the scan identical, except we have to compensate for the lower dose rate at the detector. So we have to slow down the detector and run the same scan at a different scan speed. So now we have a focus detector distance of 1100 millimeters. You can see it right there. And we're shooting at the same parameters, 200 kV and 200 microamps. What you also see is now the detector is running at 3 hertz, so that's 3 frames per second, opposed to the other scan we had it at 12 frames per second. So that's where the speed difference is, and in order to compensate for the focus detector distance, in order to have the histogram in the same spot, you gotta slow down the detector, and that's where the difference in speed comes from. Everything else is the same. We have about 100 micron voxel size, so exact same geometrical magnification, and this is 2.75. Both scans identical except the focus detector distance. So in this scan, opposed to almost 3 minutes, I think it was 250 or something, or 230, now we're looking at 11 minutes or 10 minutes roughly scan time. So that's the difference. We're talking speed here. So now I brought the scans up in VG Studio Max, and you can see we see some porosity here. And if I switch between the 2.5 minute scan, which is this one, and the 10-minute scan, which represents the 1100 millimeter focus detector distance and the 550 millimeter focus detector distance, I don't see any difference. It's the same magnification, the same voxel size, and yeah, I manually adjusted the contrast, so that's why there's a little bit of difference, but that's more me. That's one view where you can see the porosity, same quality. For things like that, you rather scan it at closer focus detector distance, so you don't spend 10 minutes versus 2.5 minutes. If you look at another slice, there's more porosity here, and of course you can see some artifacts here, but that's expected at 2.5 minute scan time. And if you switch back and forth, same artifacts are there, same porosity shown. So from a glance, and it's even at 2.5 minutes, that's even good enough to do a little bit of segmentation. I spent a few minutes to do this. So now we looked at our carburetor and can see defects, and we can visually judge if we're happy with it or not. But now the argument for a larger focus detector distance is, do I lose accuracy, or does it get more distorted, or what? So in order to look at this aspect, I'm going to scan this, what we call wedding cake, 4 times. Going to scan it at 550 millimeter focus detector distance first, twice. So I put it in, I scan it, leave it in, scan it again, same everything, same parameters. The reason is I want to be able to see the difference from scan to scan, and if we wouldn't do at least 2 scans at each position, we would mix 2 problems. One problem is maybe there's a distortion that occurred because of the different geometry, or something in the reconstruction could be off. I just want to eliminate that, or at least I want to know if we have an issue there. That's why I do that, and then we can compare all the scans and see what is the difference between the scan, the same position with everything the same, and compare then against the scan with the other focus detector distance. What's used in aerospace quite a bit, alloy. And I machined this, and it's not perfect. It's a decent lathe, but it's not a state-of-the-art, high accurate lathe. So it's not perfect round, but it's good enough for our application. And also keep in mind, we're doing this at 36 second scan time, so that means accuracy, or the resolution, will be in the same range of about 100 micron voxel size. So it's not crazy accurate, but we'll see the effect of our experiment in this, I think, pretty good. So I put this in an angle, and we just push the button and start the scan. So now we scanned the wedding cake 4 times, 2 scans at 37 seconds and 2 scans at 122 seconds. The reason I did that is to do a more quantitative analysis, opposed to what we did with the carburetor, where we just looked at images and say, yeah, that looks the same. It starts first with a visual inspection, and we just switch between the 2 scans, and they're both good, pretty clean. We have a good histogram here, pretty happy with that. So for analysis, what I did is I created a line on the inner edge of the inner cylinder here. So, and that's a sharp edge, and it's supposed to be, you know, the smaller the edge is, the better. So if you're looking at the line profile here, and you're going to see this up here, that's the cross section we're gonna do this on, and it's going from, you know, this side of the edge through the center hole to the right hand side. And what I did is I copied and pasted that line to the other scan, so the lines are at the exact same location on all the scans. So what I want to measure is the edge here. So I'm going to move that line here to where, you know, I think it reaches the peak before it goes down, and that's right around there. And then can zoom out a little bit and move that line closer, and I zoom in and I place that right where this falls. And yeah, you can do that on all the scans. And what I found is that the deviation is in the 50 micron range from this one scan to the other. Another thing we can do is we can do a comparison between all the scans. So first let us compare the two scans I did in either position. So at 550 millimeter focus detector distance, and compare that to the second scan at the same focus detector distance, which is shown here. You can see a pretty, you know, steep peak in the histogram. So this is the deviation, and we see a standard deviation of maximum deviation of 37 microns, which is expected. Again, this is about 100 micron voxel size and 2 scans, and that's about the deviation you would probably expect scan to scan. So if we can compare that to the 122 second scan, you can see it's not as steep, but we still have a maximum, or we have a maximum deviation of 75 microns. It's less, but it's still pretty close. And it's always the question, what do you want to do? What's the accuracy you expect from your scan? So another way to look at this is to create a circle, and I did that here. And if we want to look at our fit points, you can see the deviation to that circle of 3.2834 millimeters radius. So that's where our fit points are. And if you right click here and go to properties, you can see the form error is 35.8 microns. That gives us a form error of 35 microns. If I do the same on the other scan, we have a form error of 46.4 microns. Again, this is not the same. It's a little better on the 1100 millimeter focus detector distance scan, but it's not a lot. And again, you're saving time, and this is a lot. From 550 to 1100, you can scan 4 times faster. So another thing you can look at is the actual size deviation difference between the two scans. And I did this just for one example. Is this circle that I just did. So that circle here in this 37 second scan is 3.2834 millimeter. Again, this is radius. If I go back to this one, this is 3.2798. So we have a deviation of 3.6 microns, which is not a lot. So again, we're looking at a scan and 100 micron voxel size, and we have a deviation from one scan to the other
of 3.6 microns. And again, this was fairly quick, 37 seconds versus 122 seconds. I didn't want to spend too much time, but if you spend more time, this is going to get more accurate. Of course, you can probably get down to a few micron or 50 micron, 20 micron or less voxel size, and you will probably see similar effects on the results. But I think that shows us that, don't waste too much time using large focus detector distances. Start with something small and then look at your accuracy later and do your analysis, if you want to use the VDI-VD 2630, you can analyze the uncertainty of measurement for your scans, and you'll see that you're probably, even for most cases, are good enough with smaller focus detector distances and faster scan speed. I just want you to be aware that you may be spending more time using larger focus detector distances than you really need, because you save time, but you don't gain that much. If it is about the last micrometer, yes. I use short focus detector distances a lot, and that's my first try. If I do something, I go as quick as possible. And for most of the applications, that's what you want to be able to do. So make sure to use the advantages of small focus detector distances if you have the ability.